Hello, this is Jennifer Martinez, and in this video we're going to talk about the characteristic equation. What is the characteristic equation? The characteristic equation of an n by n matrix is the scalar equation determinant of a minus lambda I equaling 0. It's just that equation. And we're going to see that lambda is an eigenvalue of A if and only if lambda satisfies the characteristic equation. Why? Well, if you remember the definition of an eigenvalue, lambda is an eigenvalue if there is a non-trivial solution, x, of the equation ax equals lambda x. So, if you remember what we did in the last video, we subtracted over that lambda x. And we factor out an x. So we're looking for non-trivial solutions to this. And we know by the invertible matrix theorem that if an equation, the homogeneous equation, only has the trivial solution, then this is invertible. But we want there to be non-trivial solutions. Therefore, we can say that by the intermediate value theorem, A minus lambda I. And if you remember from determinants, we know that when a matrix is invertible, we know that the determinant is not equal to 0. So therefore, if it's not invertible, it must be equal to 0. And by the way, we could actually change these to if and only ifs. So it works. The invertible matrix theorem was all if and only if statements, so it does work. Here's the theorem that states that if you let A be an n by n matrix, A is invertible if and only if the number 0 is not an eigenvalue and the determinant of A is not 0. So let's look at an example. Example 1. Example 1 says to find the eigenvalues of this matrix. And again, we can know that lambda is an eigenvalue if and only if it satisfies this equation. So let's look at that equation. So the determinant of A minus lambda I, what is that going to be? Well, let's just look and see what A minus lambda I is. So if I subtract those two matrices, it again only affects the diagonals 2 minus lambda and then negative 6 minus lambda. And then 3 minus 0 will stay the same, and this one will stay the same. I'm going to set that equal to 0. So to find the determinant of this, we know we are going to multiply. I should probably keep it a matrix. And then what do we get? We know A times D, the formula for a 2 by 2. Minus B times C. This is called our characteristic equation. So we can use this characteristic equation to find the eigenvalues. We can FOIL this out, combine like terms. So I'll put the lambda squared first, and I would have a plus 4 lambda, and that would be a negative 21. We can solve this by factoring. Oops, sorry. So a plus and a minus. So we can see there are two values, two eigenvalues, negative 7 and 3. And you could check these, which we did in our last video. So next is a theorem, actually from the last section, that says the eigenvalues of a triangular matrix are the entries on its mean diagonal, which was pretty easy to prove before this section, but now it's even easier. So For simplicity, let's just consider the 3 by 3 case. If A is an upper triangular matrix, or it could be lower, it doesn't really matter, but you can see A minus lambda I is still going to be a triangular matrix, and here it is right here. If you look at the determinant of that, we know that the determinant of a triangular matrix is just the entries, the product of the entries on the main diagonal. And we know from what we did above that determinant, this characteristic equation, must be 0. So you can see here that A11 must be lambda, or A22. I could just say it the other way around. The eigenvalues are just the entries along that diagonal. So let's look at an example of this. It says you can see this by this example because it says actually not to find the eigenvalues, but to find the characteristic equation. So let's go ahead and do that. Let's look at the determinant of A minus lambda I. And you can see here where the only thing that changes is this diagonal. So this time I'm not going to show the work. I'm just going to write down what that equation is. So along the diagonal, it's going to be 5 minus lambda, 3 minus lambda. These zeros are still going to be here. And these numbers are still going to be there. That's because we're going to subtract the identity, and that's not going to change. It's only going to change the diagonal. It's only going to change. These stay the same, these stay the same. And we're going to set that equal to 0. So we're going to get, or, might as well put these together. So you're going to see that lambda is going to be 5, 3, or 1. Those are the 3 different eigenvalues. And they say in this example, because of the squared here, that the eigenvalue 5 is said to have multiplicity 2. Because again, lambda minus 5 occurs 2 times as a factor, of the characteristic polynomial. So in general, the algebraic multiplicity of an eigenvalue, lambda, is the multiplicity as a root of the characteristic equations. Let's look at an example of this in the book. Example 4 says the characteristic polynomial, they're giving it that to you, of a 6 by 6 matrix is this expression. Find the eigenvalues and their multiplicities. So again, they're already giving you the characteristic equation, and they want you to find their eigenvalues. So all we need to do is set this equal to 0. So what they did here is they factored out what was common, h to the 4th was common, and they factor out this trinomial. And they realized that the factors, or the solutions to this equation, are lambda 0, 6, and negative 2. And since there's a 4th power here, this is multiplicity of 4. That is the answer. They have a note here that I would like to read. It says you could also list example 4 by repeating the zeros 4 times, so that it shows that the eigenvalues are repeated according to their multiplicities. Because the characteristic equation for an n by n matrix involves the nth degree polynomial, the equation has exactly n roots counting multiplicities, provided complex roots are allowed. And complex roots are allowed, by the way, and they're called complex eigenvalues. But in this video, we will only consider real eigenvalues, and the scalars will continue to be real numbers. So that concludes this video.